guys, welcome to another video in the series of coding. Today we are going to do the problem which is called nodes at even distance. So you are given a connected acyclic graph with n nodes and n minus 1 edges. You have to count the pair of nodes that are at even distance from each other. Let's try to take some example to understand this. Let's take this example. So this is a graph that is given, and in this graph you have to count the nodes that are at even distances from each other. So what do we mean by even distances? So even means distance of 2, distance of 4, distance of 6, distance of 8, distance of 10 and so on, right? If they are at these distances from each other, then they will be even distances. So let's try to take an example. So let's say the node 1, if we see the node 1, it has one edge with 2. This is at a distance of 1. This is odd, right? But if we see 1 and 4, between 1 and 4, if you notice, there are two edges in between them, right? There are two edges in between them. So if you see the pair 1, 4, they have two edges in between them. That means that the nodes 1 and 4 are at even distances from each other, which is asked in the question, right? So 1, 4 is one of the examples. So the node 1 and the node 4, between them there is even distance or even number of edges. Okay, there is another example. If you see node 2 and node 3 in this case, then also you can see that there are two edges in between them, right? There are two edges in between node 2 and node 3. So in this problem there are two answers, 1, 4 and 2, 3 for this particular example. Okay, now let's try to take some other example. So in this example, let's try to find out what are the nodes which are at even distances from each other. So let's try to note step by step, right? Let's say you start counting for the node 1. If you see with the node 1, you can see that the node 5 is at even distance, right? For the node 1 you have node 5, and for the node 1 you have node 3 also. See, both of them are at even distances, right? There are two edges between 1 and 3 and 1 and 5. Okay, so you can count the node 1, 5, you can count node 1, 3. There is also this node 7. You can see 1, 7. If you see, there are 1, 2, 3, 4 edges between 1, 7. 4 is also an even number, right? So between 1 and 7 also there are even distances. Now let's quickly count for the node 2. So if you see for the node 2, if you see node 2 with node 4, there is even number of edges between them. So node 2 and 4. Similarly, if you see node 2 and 6, there are again even number of edges between them. Similarly, I think that's it for 2. Now let's start for 3. So if we see for 3 with 5 will be one of the answers. 3 with 1 will be one of the answers, right? Both of them have even number of edges between them. Also node 3 with node 7. Here also there are two edges. So for 3, these are the possibilities. Now let's note for node 4. So if you see for node 4, you will have 4, 2 as one of the answers. You will have 4, 6 also, which has even number of edges between them. I think that's it for 4. Now let's note for node 5. So if you see for node 5, 5 and 1 will be one of the answers. 5 and 3 also has even number of edges between them. Node 5 and 7 also has 4 edges between them. So again that is also even. So I think that's it for node 5. Now let's note for node 6. For node 6, if you see node 6 and 4, if you see node 6 and 2, if you see node that's it, I think. Now let's see for node 7. So if you see for node 7, let me write here. So for node 7 you have node 5, which has 4 number of nodes between node 7 and 5, 4 number of edges. Similarly, between node 7 and 1 also there are 4 edges, right? So, and for node 7 and 3 there are only 2 edges. So again that is also even. So these are all the possible answers, I think. Let's count the number of answers that we have got. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So do we really have 18 as the answer? So in this case we are getting the answer as 18, but actually we are counting nodes 2 times. How are we counting nodes 2 times? For example, you have seen 1, 5 and you are also writing 5, 1. So if you have taken 1, 5, you need not take 5, 1 again. Similarly, if you take 1, 3, you need not take 3, 1. If you take 1, 7, you need not take 7, 1. If you take 2, 4, you need not take 4, 2. If you take 2, 6, you can ignore 6, 2, right? And similarly, if you take 3, 5, you need not take 5, 3. If you take 3, 7, you need not take 7 3. If you take 4 6, you need not take 6 4. If you take 5 7, you need not take 7 5. So actually what is the answer? There are only 9 such nodes, right? 1 2 3 4 5 6 7 8 9. So 18 by 2 is 9. So actually we just have 9 such nodes which have even distances between them. Now let's try to think of what approach can we use to solve this problem. Let's think of the brute force approach that we can use to solve this problem. So the brute force approach is go to each node and then count the distance between each node by going to all the other nodes. Remember, this is a connected graph. This is a connected acyclic graph. Okay, that means that you can, from one node, you can travel to any other node. So if you, from one node, if you travel to any other node, what will be the time complexity? It will be V plus E, right? It will be V plus E to do a DFS or a BFS based traversal algorithm. But you are doing it for each node, right? So for example, you go to the node 2 and then count the distance of it from all other nodes. Similarly, go to node 5, count the distance of it from all other nodes, and so on. So if you do it for each of the nodes, it will be V into V plus E. Now there is a bad time complexity. We want to improve it, right? So the brute force solution will not work for big test cases. So what we'll do, we'll try to improve our algorithm. So what if we store the distances? What if we store the relative distances by making any node as a base node or a root node, right? And from that, what if we store the distance of all other nodes? So what do I mean by that? So first let me write the distance array. So we have the nodes 1 2 3 4 5 6 7. Okay, now let me make any node as root node, right? Any node of our choice as root node. Let's say I make 3 as root node. Okay, you can make any node as root node. Now let's assign it a distance of 0. Okay, now let's go to all other nodes and find the distance just using one single traversal. Just in one traversal, we need not do any other traversal, just in one traversal, right? Which the time complexity is V plus E. You can either do BFS or you can do DFS, any traversal algorithm that you like, and just find out the distance of this root node from all other nodes, and you can make any node as a root node. Okay, so let's say 3 is at a distance of 0. Now let's see 6. So between 3 and 6, there is one edge, right? So 6 is at a distance of 1. Between 3 and 4, there is one edge. So 4 is at a distance of 1. Between 3 and 7, there are two edges. So 7 is at a distance of 2. Between 3 and 2, there is one edge. So 2 is at a distance of 1. Between 3 and 5, there are two edges. So 5 is at a distance of 2. Between 3 and 1, there are two edges. So 1 is at a distance of 2. Now once we have this distance array using just a single traversal, right? In this distance array, if you just see the nodes that are at even numbers, right? For example, 2 2 2 0, all these nodes 1 3 5 7, if you see all the nodes 1 3 5 7, if you see these nodes, they are at even distances, right? They are at distance 0 2 2 and 2. All these are even distances, right, in this distance array. So relatively all are at even distances compared to each other. That means all of them, right, all of them are going to be at even distance with respect to each other also. See, why is it? Because 1 with respect to 3, okay, 1 with respect to 3 is at even distance. It's very important to understand this. 1 with respect to 3 is at even distance, right? And 3 with respect to 5 is also at even distance. So obviously 1 and 5 are also at even distances with each other. Okay, so it's very important to understand this. See, between 1 and 3, okay, let's take a simple example, then it will be much more clearer. See what do I mean by that? Between 1 and 3, if you see, between 1 and 3, let's say there are two edges. Okay, simply it means between 1 and 3 there are two edges. So 1 and 3 have two edges in between them. Between 3 and 7 also there are two edges. So if 3 and 7 are at even distance, 1 and 3 are at even distance, that means 1 and 7 are also at even number of distances between them, right? They also have even edges between them. Okay, similarly, if you see 1 and 3 have even edges between them, 1 and 5 have even edges between them, that means what? Relatively 1 and 5 also has even edges between them, right? So this is the logic. So once you have made the distance array, it's very easy. Okay, so why is it very easy? Once you made the distance array, see all those edges which are at even distance. Okay, so how many edges are there? There are 4 edges which are at even number of, okay, 4 edges which are having even distance. Okay, these are 4 edges which are having even distance. Okay, what are those 4 edges? 1 see what are the 4 edges? 1, 3, 5, 7. They have even distance, right? So 1, 3, 5, 7. Now you see in this graph, we had already made the graph. 1, 3, 1, 5, 1, 7, 3, 5, 3, 7, 5, 7. All these edges are at even distances between them, right? So that is what we did here also. So you know, you have 4 pairs. If you have 4 pairs, all are at even distances, just do 4c2. What is 4c2? What is 4c2? 4 factorial by 2 factorial, okay, 2 factorial. This is 4c2, right? What is 4c2? So let's just solve 4c2. So this is 4 into 3 into 2, and below you have 2 into 2. So what will be the answer? So 6. So you have got 6 edges, right? So if you just simplify nc2, what is nc2? If you just have any nc2, if you just simplify this n factorial by 2 factorial, so if you just simplify, it is actually n into n minus 1 by 2, right? So that's what it is. So if you want to solve 4c2, 4 into 3 by 2, which is just 6, okay? So you have got 6 edges, and you can see here 1, 3, 1, 5, 1, 7, 3, 5, 3, 7, 5, 7. 6 edges which are at even distance with each other. How did we find it out? Very easily. We just looked at our distance array and we found it, okay? So we have seen for the even edges. Now let's see for the odd edges, okay? This will work even for odd edges, okay? Now let's see all the nodes which are at odd distances relatively from each other. So node 2, node 4, node 6. All are at odd edges, okay? Relatively. So if 2 and 4 are relatively, they have odd distances between them, means actually, see what does it mean? Let's see the example. The node 2, node 4 and node 6 are relatively all having odd edges compared to node 3, okay? That means, see, compared to node 3, the node 2, the node 4 and the node 6, all these three nodes are having odd distance compared to node 3. That means amongst each other they will have even distances. See, it's very important to understand this. Let me take a brighter color. Let's say compared to node 3, the node 2 is having a distance of 1. Compared to node 3, node 6 is also having a distance of 1. If you see between node 6 and node 2, they are having a distance of 2, okay? They are having a distance of 2. There are 2 edges between 2 and 6. Let's see it again. Between 2 and 3 there is 1 edge. Between 6 and 3 there is 1 edge. Between 6 and 2 there are 2 edges, right? That means relatively 6 and 2 are at even distance with each other. So this is our answer, okay? So similarly we can write for those nodes which are having odd distances. What can we write? Node 6, node 2 and node 4 are all relatively going to have even distances between them. See, all of them have 2 edges between them. Okay, so between node 2 and 4 also there are 2 edges. Between node 4 and 6 also there are 2 edges. Between node 2 and 6 also there are 2 edges, as you can see in this diagram. Okay, so how many nodes are there now which are having odd distances? There are 3 nodes. So among them they are having even distances between them. So 3c2 will be the answer. What is 3c2? N into n minus 1 by 2, right? So there will be 3 edges which are having even distances relatively. Already we had found 6 edges. Now we found 3 more edges. So 6 plus 3, 9 is our answer. Okay, so this is how we are going to solve this problem. Now let's quickly move forward to coding it. So you can use any traversal algorithm, whichever you like, BFS or DFS. Let's just quickly solve it using BFS. So for BFS you need a queue, and what else do you need? You need a distance array. So you can make any node as root node, and then in the distance array you can see which nodes are at even distance relatively compared to each other and which nodes are at odd distance. All these will form pairs. Okay, all these will form pairs, and you can find out the total answer. Okay, so vector int distance, and then we can also store a visited array. Whenever we do a traversal algorithm, we also have a visited array. And initially I make all the values as false. Initially all the distances are 0. Okay, now what I'm going to do, I'm going to make any node as my root node. Now there can be nodes which have just one root node, right? So I will just make one as my root node so that it works for all examples. Okay, so let's take some other example quickly so that we make sure that this concept is very clear. Okay, so let me take one quickly, some other graph. Let me take some other graph. 5, 6, 7, 8. okay, some graph like this. So this is a graph. Now we have to find out what are the nodes which have even distances between them. So what are we going to do? What are we doing? We are making a distance array 1 2 3 4 5 6 7 8, right? So this has 8 nodes, right? Now you can make any node as root node. Let's say I make the node 1 as root node. So what I do, 1 is at a distance of 0, right? Now let me quickly see for all other nodes. So between 1 and 2, it's a distance of 1. Between 1 and 7, again it's a distance of 1. Between 1 and 8, it's a distance of 2. Okay. Between 1 and 3, again it's a distance of 2. Between 1 and 4, it's a distance of 3. Between 1 and 5, it's a distance of 3. Between 1 and 6, it's a distance of 4, right? So I made the distance array. Now when I made the distance array, what am I doing? Now just see the distance array. All those nodes which are having even, first let me see all those nodes which are having even numbers stored in the distance array. So all these are even numbers, right? How many nodes do I have? I have 4 nodes which are having even numbers. So all the nodes 1, 3, 6 and 8, all these, there are 4 nodes which are having even distances between them. So relatively, if you see 1, 3, 6 and 8, okay, if you see any of the nodes, okay, see the nodes 1, 3, 6, 8, either you take 1, 3 pair or you take 1, 8 pair, right? If you take 1, 3 or if you take 1, 8 pair or if you take 3, 6 pair, anything, right? All these nodes amongst each other they will have even distances, right? So that is the simple logic. So how many nodes did we have? We have 4 nodes. Now if amongst each other, how many pairs will be there amongst each other? If you see, there will be 4 C2 pairs. And what is 4 C2? It is just 4 into 3 by 2. So how many pairs do we have? We have 6 such nodes, 6 such nodes with even distance between them, right? But this is not the only answer. Now you once you have seen the even distances, you can also see the odd distances, right? So what are the odd distances? Node 2, node 4, node 5, node 7, all are at odd distances. So you see they have odd numbers stored in the distance array. So how many such nodes are there? Again you have 4 nodes, right? So the nodes 2, 4, 5, 7. So you can see here nodes 2, 4, 5, 7. All these nodes, you can take any pair in between them. For example, if you take the 4, 7 pair, you can see that it is having 4 edges between them, which are again even number of edges. Similarly, if you take 2, 5 pair, any pair you can take in this set, they will all be at even distances, right? So if you take the 2, 5 pair, it has two even edges between them, 2 edges between them, right? And so on. So any pair within this set of 4 also will have even number of edges. So again you have 4 C2, right? So 4 C2 is again 6. So 6 plus 6, 12. 12 will be the answer in this case, okay? So this is the logic, this is the concept that we are using. Now let's quickly move to code. So what we did, we declared a queue, we declared a distance vector, we declared a visited vector, and for simplicity's sake, okay, and to so that it's valid for all the test cases, I am pushing the node 1, okay? Now let's quickly do the BFS. While not of queue.empty, what we are going to do, what do we do in the BFS algorithm? See, whatever node we have at the front, first of all we take that. So the node that we have at the front will be the node, okay? Now when I'm pushing 1, I will also make its distance as 0, right? So its distance is already 0, so I need not explicitly give distance of 1 as 0, but it's understood, right? It's understood because initially all the distances are 0. So what I'm going to do here, I'm going to take the distance. What is the distance of the node that I am looking at? So distance, from the distance array I will get the distance, okay? Once I have done this, what I'm going to do, I'm going to pop it from the queue and I'm going to traverse all its neighbors, right? So what are we doing? We are doing a simple BFS traversal algorithm, right? Simple BFS. You can do it using DFS also. Both will give the same time complexity, okay? So now what I can do, I can traverse all its neighbors. So for int neighbor, I am given a graph. As my input. So in this graph we can traverse each of the neighbors. So I traverse the graph and I traverse each of this neighbor. Now if my neighbor is not visited, right? If my neighbor is not visited, so initially I will have to make visited of 1 as true. Now if my neighbor is not visited, right? If my neighbor is not visited, so then I can traverse it. So what I'm going to do, I'm going to push it, I'm going to push the neighbor in the queue, and what I'm going to do, I'm going to increase its distance. See, if the distance of this node let's say if the distance of this node is 0, so I see the neighbor, all the neighbors of this will be at distance 1. If the distance of this node is 4, then all this will be at distance 5, because these are just immediate neighbors, right? These are just immediate neighbors. So what I'm going to do, distance of neighbor is just equal to distance plus 1. Okay, that's it. Now I'll also make it visited. So visited of neighbor is equal to true. That's it. That is the simple BFS code that we have written. Now when we exit, right, when we exit from this, what we have to do, we have to count all the total number of nodes that are at even distances relatively and odd distances relatively, right? So if distance of I is even, that means mod 2 is equal to 0, then let's say I increase the even distances, else I increase the odd distances, right? So this is what I'm doing. So initially let me give two variables, even is equal to 0, odd is equal to 0. Now what I do, after this I can just very easily return the answer. What is the answer? Even into even minus 1 by 2, because n into n minus 1 by 2, what is this? This is just nc2, right? If you do nc2, you will get n into n minus 1 by 2. Similarly, if you do odd into odd minus 1 by 2, you will get the answer. Okay, now let me just run and see if it's going to work. There's some compilation error, neighbor was not declared in the scope. Where is the error? Let's see. Visited of neighbor is equal to true, so I have not given a h. Okay, now let's run and see again. So it's working. Let's submit and see if it will work for all the possible test cases. So it's working. Thank you for being